Hello and welcome back to the channel. Today we're going to be going over a brief introduction to interrupts. Be sure to like and subscribe so you can stay updated on more videos. Let's get right into it. So in computer systems, an interrupt is a signal that momentarily suspends the current program's execution to allow the CPU to address a higher level priority task, such as managing input-output activities or responding to hardware events. Interrupts can be caused by either hardware, such as keyboard inputs, mouse movements, or timers, or software, such as system calls or exceptions. Once the interrupt has been handled, the CPU resumes execution of the interrupted process. This method increases system efficiency by enabling multitasking and decreasing the requirement for constant polling. Interrupts in computer systems can be categorized into three main types: hardware interrupts, software interrupts, and exceptions. So hardware interrupts, these are signals that are sent by external devices such as keyboards, mice, or network adapters to notify the CPU of an event requiring immediate attention. They can be further classified as maskable, which can be ignored or delayed based on the priority, and non-maskable, which are critical events like hardware failures that cannot be ignored. Next type is software interrupts. These are triggered by programs using special instructions to request system services such as system calls in an operating system. They allow user applications to interact with the kernel, enabling functions like file access and memory management. And our third type is exceptions. These occur due to errors or special conditions during program execution, such as divide by zero errors, invalid memory access, or illegal instructions. Exceptions can be faults, which are recoverable, allowing the program to retry the operation; traps, which are intentional debugging breakpoints; or aborts, which are severe errors that terminate the process. Interrupts are essential for controlling concurrent process because they allow the CPU to effectively switch between tasks, ensuring that high priority actions receive prompt attention without interfering with the other processes. They also improve system responsiveness by allowing real-time handling of events such as user inputs and hardware requests, rather than needing constant polling, which would otherwise waste processing resources. When handling an interrupt, an operating system always follows the same steps. First being an interrupt occurrence, which is where the CPU receives a hardware or software interrupt signal, which will pause the current program in execution. Next is your interrupt acknowledgement. The CPU will identify the interrupt and determine its priority, usually with the assistance of an interrupt controller. Next is the saving context. So the current state of the running process, including register values and the program counter, is preserved so that it can be resumed later. Next up is your interrupt service routine execution. So to process the interrupt, the CPU invokes the relevant ISR, which is your interrupt handler. Next is your restoring context. So after the interrupt, the save process state is restored and finishes with resumption of execution. So the CPU just resumes normal execution of the interrupted process or shifts to a different task as directed by the scheduler. So interrupt prioritization guarantees that crucial activities such as hardware breakdowns or real-time system events are prioritized above less urgent ones. The interrupt controller handles this by assigning priority levels and deciding which interrupts should be addressed first. High priority interrupts can be preempt lower priority ones, enhancing system responsiveness and avoiding delays in critical operations. Proper prioritization improves overall system efficiency, whereas bad management can result in bottlenecks, excessive context switching, or priority inversion, which occurs when a lower priority activity blocks a higher priority one. Interrupt controllers and interrupt masking are technologies used by these systems to effectively handle and prioritize interruptions. The Programmable Interrupt Controller, PIC, or Advanced Programmable Interrupt Controller, APIC, decides which interrupt should be addressed first, depending on the predefined priority levels. Interrupt masking is also used by the operating system to temporarily disable lower priority interrupts while a vital one is handled, thus preventing conflicts. Furthermore, interrupt-driven scheduling ensures that real-time and high-priority jobs receive quick attention, which improves system responsiveness and efficiency. Interrupt service routines are specialized procedures that run when an interrupt occurs, performing responsibilities such as processing input, managing hardware demands, and addressing faults. Each interrupt is assigned a specific ISR, which the CPU invokes upon detecting the interrupt signal. ISRs are critical to interrupt management because they provide quick answers to system events, enabling effective multitasking and real-time processing. Their effective implementation reduces processing delays, protects against system crashes, and guarantees that concurrent processes run smoothly. An interrupt service routine uses a structure sequence to handle interruptions quickly while maintaining system stability. Its main actions include interrupt acknowledgement, where the CPU detects and acknowledges the interrupt and decides which ISR to execute. It then saves the context, so it saves its current state, including register values in the program counter. Interrupt answering, so the ISR performs its critical tasks such as processing input, answering hardware requests, and addressing problems. It then clears the interrupt to prevent recurrent triggering. The ISR either resets the interrupt flag or sends an acknowledgement signal, and then it restores the context, so the saved process state is reloaded, allowing the system to restart execution from the point at which it was paused. So writing your ISRs presents various challenges, including minimizing execution time. So the ISRs must be quick to avoid delays and keep the system responsive. Blocking operations should be avoided in ISRs to prevent system disturbance. Data integrity. ISRs must handle shared resources with caution to avoid race situations and data corruption. Managing nested interruptions. So ISRs must effectively manage nested or simultaneous interruptions, prioritizing high priority jobs and avoiding conflicts. These issues necessitate careful design to provide prompt, stable, and dependable interrupt handling. As mentioned earlier, interrupt controllers manage and prioritize interruptions by selecting which interrupt should be handled first, resulting in efficient handling in systems with various interrupt sources. They act as a bridge between the hardware devices and the CPU, guiding interrupt signals while maintaining priority levels. Common types include the PIC and the APIC, which enable interrupt masking and prioritization. This management improves system performance by swiftly managing key interrupts and reducing conflicts in multitasking contexts. So common interrupt controller architectures include the programmable interrupt controller, the PIC, the advanced programmable interrupt controller, the APIC, and the nested vectored interrupt controller, the NVIC. So the PIC, originally employed in older systems, it allows the CPU to handle various interrupt sources by prioritizing them. The 8259A PIC, for example, can handle up to 8 interrupt lines and enables masking, which disables lower priority interrupts so that higher priority ones can be processed. It also supports interrupt chaining, which allows it to manage more than 8 devices by joining multiple PICs together. The APIC, the sophisticated programmable interrupt controller, is used in more modern multi-core processors. The APIC includes sophisticated capabilities such as multi-layer interrupt management and multi-core support. It includes the local APIC for each CPU core, which allows for efficient interrupt routing, as well as the IO APIC, which handles interrupts from external devices. APIC also enables vectoring, which involves explicitly mapping interrupt service routines to specific interrupt vectors for speedier handling. So the nested vector interrupt controller, used in ARM-based microcontrollers, allows for nested interrupts with priority and vector-based processing. It enables higher priority interruptions to preempt lower priority ones, making it ideal for real-time applications. The NVIC is extremely efficient in embedded systems since it supports low latency interrupt processing and can accommodate up to 240 interrupt lines. Interrupt controllers are essential for properly managing interruptions by prioritizing them, ensuring that higher priority jobs are serviced before the lower priority ones. Modern controllers such as the APIC offer multi-core processing, which distributes interruptions across processor cores to prevent bottlenecks and improve parallel performance. They also enable the masking of lower priority interruptions to improve CPU resource utilization during crucial processes. Modern interrupt controllers with capabilities such as vectoring and interrupt nesting reduce latency and assure the fast reaction times, which is crucial for real-time applications.